with that, allow me take a minute and remind you about the topic you are going to be dealing with. Before that, allow me greet a few people. Luze Arthur, that is another my fellow chemistry teacher at Kitende. Ochan Calvin, teacher at Kodai School, and Apollo. Guys, you are good friends. Please do the same job we are doing here. Continue teaching the learners even when they are at home. Today we are going to look at boiling point elevation of solutions. Slide 4. Boiling point elevation of solutions. As we continue with corrugative properties. Okay? So the main topic is corrugative properties, but the subtopic we are going to look at today is the boiling point elevation of solutions. So what do we need to achieve in today's lesson? Slide 7. We are going to, by the time this lesson ends, I want every student to make sure that you are able to describe the boiling point elevation of solutions. You are able to determine the relative molecular mass of a solute in a solution. Okay? If you are able to do that, then we shall end that day. For those who have not been able to access the lessons in time, please, you can visit our website on slide 6. Our website is www.kodaischool.sc.ug, or you visit the top television page for the videos. Okay? Visit the website. You can take time. When you reach on the website display, you can create an account, you sign up, you put all your details. If you don't have an email, please make sure you get an email. You put your details, you put your telephone number and your full name. Okay? We shall be able to approve your account within 10 minutes. Then you go back and log in. Okay? Log in, you reach a display which is called a dashboard. You scroll around. You see where there are classes. You pick the class you want to see the work for. Then after seeing the work, read the instructions. You either download if the instructions are saying download, or you read, or you do the assignment or a quiz. Okay? So that is it. If you fail to access, you can contact me and I guide you, because some students have been complaining. However, others have been successful. I'm so grateful to those ones who have managed to reach the work where it is. Those who have not yet managed, please try. I know others are lazy. When they reach somewhere and fail, they just leave. Please make sure you contact me and I guide you through. So let us look at what we studied yesterday and the other day and see how we can use it to understand today's lesson. We have been dealing with corrugative property, and we say that this one came up when someone realized that when you put a solute in, when you dissolve a solute in a solvent, the properties of the solvent change. Okay? You dissolve, you get a solute, you add it to a solvent to form a solution. The properties of that solvent change. And those properties that change, we call them corrugative properties. And we define the corrugative property as that physical property which only depends upon the number of non-volatile molecules, non-volatile particles, solute particles, present in the dilute solution. Note the word dilute solution, and note the chemical property of those particles, or the chemical nature. Okay? So we also looked at the corrugative properties themselves on the next slide. We say that we have the vapor pressure lowering of the solvent. We have boiling point on our next slide. Boiling point elevation of the solution. freezing point depression of the solution, osmosis and osmotic pressure. Let us look at those factors on our next slide. Okay, then we say that you can use these corrugative properties to determine the relative molecular mass of a solute in a solvent. On our next slide, we looked at vapor pressure lowering of a solvent. Okay, we say that vapor pressure is the pressure exerted by the vapor when it is in equilibrium with the liquid. Okay, so when we look at the vapor pressure of a liquid at a given temperature, is that pressure exerted by the vapor when it is in equilibrium with the liquid. Then we say that addition of a non-volatile solute lowers the vapor pressure of the solution. Okay, and we explained how it lowers it by reducing the escaping tendency of the solvent molecules. Okay, then we said that the lowering of vapor pressure depends or is based on the Raoult's law. And next slide is based on Raoult's law, and we were able to state Raoult's law. Okay, we said clear that is the relative lowering of the vapor pressure of a solvent, okay, when it is equal to the mole fraction of the non-volatile solute dissolved in that solvent. And we are able to summarize it like this. We said that this one, the P is the change in vapor pressure. Change in vapor pressure. And we said change in vapor pressure can be vapor pressure of the pure solvent divided by this getting vapor pressure of the pure solvent subtract the vapor pressure of the solution. You get the change in vapor pressure. Okay, so that's how we summarized Raoult's law, and we are able to break down the mole fraction. Okay, so when we continue on our next slide, we saw what we got after breaking down the mole fraction. Okay, we got the expression on that slide. You can see there is expression giving mass of solute multiplying by, you say mass of solute multiplying by relative molecular mass of the solvent divided by relative molecular mass of solute times the mass of solvent. Okay, that's what we got. So all that one was discussed yesterday and the other day. So today, majorly, we are going to look at boiling point elevation of solutions. We can call it a bryoscopy. Okay? Then, having looked at each and everything, remember we said that we shall be defining these terms or describing these things in one way or the other as we continue with our lessons. Okay, so today let us look at what is boiling point, what is meant by boiling point of a liquid. We see that boiling point of a liquid is the temperature at which the liquid's vapor pressure becomes equal to the external atmospheric pressure. Okay, temperature at which the liquid's vapor pressure becomes equal to the external atmospheric pressure. That is the boiling point of a liquid. Also below it, we can see that when we dissolve a non-volatile solute in a solvent, the boiling point increases. Okay? The boiling point increases or elevates. Elevation means increasing. Okay, So the difference, look at the difference between the boiling point of the solution and the boiling point of the solvent is what we call boiling point elevation of the solution. Okay? Boiling point elevation of the solution is the difference in boiling point. Okay? So here we have the difference in boiling point is the boiling point elevation. Okay? This is what we call boiling point elevation or ebullioscopy. When you meet the word ebullioscopy, when they say define this word, just know they are referring to boiling point elevation. That's what they are asking for. So don't be confused. Then we can see why is it that when you add a solute, why is it that when you add a solute into a solvent, the boiling point changes? Okay? Remember, in vapor pressure, we say that the vapor pressure lowers. That means the vapor pressure of the solvent is higher than the vapor pressure of the solution. But in boiling point, we are saying that it increases, it elevates. That means the boiling point of the solvent is lower than the boiling point of the solution. Okay? So when you are calculating, make sure you be able to identify that. Okay? So when we go to our next slide, we see that we look at the reason as to why when you add a solute into a solvent, okay, when you get a solute, you add it to a solvent, its boiling point will change. Okay? Here, boiling point. The boiling point here becomes the increases. Okay? Here, if it is 100, that side will be 120, 130 or something like that. Okay? But higher than 100. So why is it that its boiling point changes? We see that when you get the molecules of the non-volatile solute at the surface of the solution, okay, they reduce the escaping tendency of the solvent. Remember, we said that is the temperature at which the liquid's vapor pressure is equal to the atmospheric vapor pressure. For the atmospheric vapor pressure, for the liquid's vapor pressure to be equal to that one of atmospheric vapor pressure, the liquid should heat to a certain temperature, or the solution should heat up to a given temperature. So once you put the solute, will hinder the balance of the two. So you need to heat the solution at a higher temperature. Okay? So once you add the solute to reduce the escaping tendency of the volatile solvent, and once the escaping tendency of the volatile solvent is reduced, that means it will require you to apply a much higher temperature. That's why the boiling point increases. Okay? So when we go to slide 15, you can look at the diagram. That diagram is showing us the variation of the vapor pressure with temperature. Okay? That the diagram is showing us the variation of vapor pressure with temperature. You can look at it clearly. On the y-axis, you have vapor pressure. On the x-axis, you have temperature. And you know temperature is an independent factor. And vapor pressure depends on temperature. Okay? So you look at the first curve, first line is for the solvent. If you look at PO, meaning that is the vapor pressure of the solvent. The vapor pressure of the solvent at the X temperature, X degrees Celsius, okay, is P naught. But when you look at that one of of another liquid, the solution 1, if you look at that one of the solution 1 is at P1, and you see that is lower than, the vapor pressure is lower than that one of the pure solvent. And for you have seen that at Z is when you get that vapor pressure. That means that solvent will only evaporate at that temperature, at that pressure. So to reach that pressure of P naught, or with the solution, you need to heat. You can see the temperature now is increasing from X to Z. Then means that the one which is at Y, okay, the one which has had a very big increase in temperature will be less dilute. The one which is very dilute is the one which is which heats up at Z degrees Celsius. Okay, so when you look at it very well, you realize that AX, look at AX, that curve, that line, it shows the variation of the vapor pressure of a pure solvent with temperature. Okay, then BZ, it shows the variation of vapor pressure of solution 1 with temperature. CW shows the variation of vapor pressure of solution 2 with temperature. Okay, then T naught is down in direction of X, is the boiling point of pure solvent. T1 is the boiling point of solution 1. That is directly at Z. However, we were not able to capture them. Sorry. So T2 is the boiling point of solution 2. That is at W. You can say W. We can say X for T1, Z for T2, Z for T1, W for T2, X for T naught. Okay, so when you look at it very well, you realize that the dilute solution, okay, the vapor pressure curves for the dilute solution are nearly parallel to that of a pure solvent. Can bring back that slide. The vapor pressure of the dilute solution is nearly, okay, parallel to that one of the pure solvent, and the curves therefore approximate to a straight line. If you can look at it, it is almost becoming a straight line. And once we say that, that means AX, BZ, and CW will be almost approximating to a straight line. AX, look at it. BZ, look at it. The CW. So therefore we look at that, we look at XYZ. XYZ, you can see it there, and XKW as triangle, as similar triangles. Okay, you can look at them, they are all centering to X. Okay, the 90, the angle of 90 is on at X there. Okay, so from geometry we are going to see on that very slide, we shall see that XZ, look at XZ, the ratio of XZ to XW will be equal to the ratio of XY to XK. I mean this one. XZ, that ratio to XW, from that curve, XZ to XW will be equal to XY to XK. Okay, you look at that one very well, so you can come back to the blackboard. Once you have this one, we are saying that they look to be similar triangles. So these lines, the ratio here is almost equal to that ratio. So we know that when we say ratio can mean xz over xw will be equal to xy over xk. All right, we can go back to that slide and we emphasize a few things. So when you look at xz is the change in temperature of solution 1. Then xw is the change in temperature, the elevation, boiling point elevation of solution 2. Then xy is the change in vapor pressure for solution 1. xk is the change in vapor pressure for solution 2. Let us look at slide 18 and see how that one is summarized. Okay? Slide 18. So on slide 18, we are going to see that all that work, that one is summarized there. xz is the change in temperature for solution 1. Change in temperature for solution 2. So once we get those values I've got already, where there is xz, we put there T1 minus T0. Where there is xw, we put there T2 minus T0. Okay? Where there is xy, we put there T0 minus P2. Supposed to be P1. Okay? Where there is xy, okay, we put there that. So let us move. When you look at your right hand side, you see that the change in temperature for solution 1 divided by change in temperature for solution 2 is equal to the change in pressure for solution 1 divided by change in pressure for solution 2. Change in temperature for solution 1 divided by change in temperature for solution 2 is equal to change in pressure for solution 1 divided by change in pressure for solution 2. So when we go to our next slide, we are going to see something different. We're going to see that when you divide the numerator and the denominator on the right hand side by P0, P0 is what? Is the vapor pressure of the pure solvent. You can see what happens there. That you divide the change in pressure for solution 1 with P0, change in pressure for solution 2 with P0. So you come up with a conclusion that when you look at that equation, the boiling point elevation of a solution is directly proportional to the relative lowering of vapor pressure in dilute solution. Okay? We mean this one, that the change in temperature, the boiling point, will be directly proportional to the relative lowering of vapor pressure. That's what we see. Okay? So when we move to our next slide, we shall compare it with Raoult's law. Remember, we already have here Raoult's law. Okay? So here, if we remove this one and say, in case if this one is equal to that, okay? And here we have also Raoult's law that the change, the relative vapor pressure is equal to the mole fraction of the solute. Here we are saying that the relative vapor pressure is equal to the boiling point elevation. Okay? So we can compare the two. Guess if we call this one, we look at this one and look at that one, we shall come up with a conclusion that this boiling point elevation is directly proportional to the mole fraction of the solute. But for this case, you can use a B there. It is not a must that you put a 2. So define your symbols, okay? That you can say, let the mole fraction of the solute be XB. You let that one to be the mole fraction of the solute. So once you have this one, you have compared this one with that one. You have seen that here you have relative vapor pressure equaling to mole fraction. Relative vapor pressure equaling to boiling point elevation. So you compare the two and you come up with this conclusion. And remember, when we have the proportionality sign, we say that the relative, the boiling point elevation will be equal to a constant times the mole fraction of the solute. K is a proportionality constant. Okay? K becomes a proportionality constant. Then when you go back to that slide, we see that what you have been doing, in the previous lesson, we were able to use mole fraction of the solvent, of the solute, to come up with a bigger expression. Let's go back to that slide and we see how. Remember, we said mole fraction equals what? Mole fraction, if we consider a solute, mole fraction of the solute will be equal to the number of moles of the solute divided by the total number of moles. Okay? So there I'm defining my terms. I'm using that NB is the number of moles of the solute. Na is the number of moles of the solvent. Okay? So when you go to the next slide, you see that once you have number of moles of the solute divided by the total number of moles, we take an assumption. On our next slide, we take an assumption that if the solution is too dilute, okay, that means if you get a cup of tea and you add there half a spoon of sugar, you not feel the sugar content. That means the number of moles of the sugar content in that solution is very small. Okay? And so if you are adding number of moles of the sugar content with the number of moles of the solvent, you'll find that the number of moles of that sugar content very small, adds nothing almost. Okay? So it's negligible. That's why you have that sign. That sign is showing you that the number of moles of the solute is very, very, very small. Okay, as compared to the number of moles of the solvent. So we tend to say that Na plus Nb will be equaling to Na alone. Okay, we approximate it. That's why we come now with the number of the mole fraction equaling to Nb over Na. Remember, we said that number of mole is equal to mass given divided by relative molecular mass. We are dealing with A-level chemistry, guys. Be able to catch up with me. Okay? This is A-level, not O-level, where we shall move slowly. Here we have to do things once and for all. What we did, we are not going to repeat it. Okay? We are just going to be applying them. We said number of moles of anything is equal to mass given divided by relative molecular mass. As you can see there, mass of the solute divided by relative molecular mass of the solute. Mass of the solvent divided by relative molecular mass of the solvent. I've defined those terms. So you come up with an expression like that. That change in the boiling point elevation is equal to the constant times the mass of the solute times mass of the solvent. Okay? The relative molecular mass of the solvent times okay? We come up with this expression that boiling point elevation is equal to the proportionality constant times mass of the solute times the molecular mass of the solvent divided by molecular mass of the solute times the mass of the solvent. That's what we come up with, okay, from this expression. From that expression, we come up with this one. All this content is got from the mole fraction, because the mole fraction is equal to number of moles divided by total number of moles. So when we go to our next slide, we are going to look at something. There are so many assumptions that are made in this. Okay? So we are saying that we look at MA, okay? MA, the relative molecular mass of the solvent, to be a constant for a particular solvent. If you are dealing with a particular solvent, that RMM of the solvent is going to be a constant. So if we have a constant MA and a constant K, that means you can make them form one big constant, which is KB. Then KB, we shall say KB is the boiling point elevation constant. We have the boiling point elevation, this one. Okay, so we now include another term, TB, which is the boiling point elevation. However, we said that if 1 mole of the solute is dissolved in 1,000 grams of the solvent, the constant is called the molar boiling point elevation constant. So we come up with this expression. KB times MB times 100 divided by relative molecular mass of the solute times the mass of a solvent. That's what we come up with. Alright? Hopefully we are together. Okay? We come up with this after putting some assumptions that this one and that one are constant. Then this solution is under what we call 1 mole of the solute is dissolving in 1,000 grams of the solvent. So that is it that you can look at. So on our next slide, we can look at the experiment, okay, that is used in determination of the molar boiling point elevation constant, or the ebullioscopic constant. Okay, that's what we look at. So when we are determination of the relative molecular mass by boiling point elevation method, okay, that is the experiment you can come up with. There are so many experiments. That's why I encourage you to go and read the textbooks. Okay, in A level, the more you read, the more things you'll get to know, or the more you know that you don't know, so you'll be forced to read. But if you don't read, you'll assume that you know. Okay, when you read, you identify that you don't know. You need to read. So it is upon you whether to read and identify that you don't know, or to leave. But for the future of our country, you need to read, because we need very many scientists. So on that experiment, first of all, you can define the molar boiling point elevation as the amount by which the boiling point of 1,000 grams of a solvent is raised by dissolving 1 mole of a non-ionizing and non-volatile solute. Okay? So that is the experiment. You can see the side arm, you can see the thermometer, you can see the control pump, and you can see the solvent. Okay? So when you look at that experiment, what should come into your mind? That a given procedure is followed. So look at it very well. You see the thermometer, you see what you do, you get a known mass of a solvent. You give it, for example, you can call it X. Okay? You put it into that tube. After putting it into that tube, you heat it. Okay? You heat it, and the boiling point of the pure solvent is measured and recorded. You get a known mass of a pure solvent, X, you heat it, and you record its boiling point. Okay? Then you add there a known mass of a solute. You can say the solute is Y. Okay? So you can say solvent I told you that any symbol you use, you let be like that. X gram, solute, Y grams. Okay? So you can let the two. You say you have the solute as Y gram, solvent X gram. Let us go back to our diagram. And we see that when you add a known mass of a solvent, a solute, into that solvent, remember you first added the solvent, now you're adding it, the solute. Okay? Then the solution, you heat the solution, you mix and heat the solution, its boiling point will increase. Remember, if the boiling point here was T1, here it will be T2. If here was T0, here it will be T1. Okay? Doesn't matter even if you say TA, TB, so long as you maintain what you let there. Okay? So once you do that, you'll be able to come up with the results. And in the results, you need to summarize. Let us look at the slide showing the results. The results we are seeing, the boiling point elevation constant, you know it. That one doesn't change. Boiling point elevation constant. The word constant is the KB that we got from the K as a constant and the relative molecular mass of the solvent as a constant. Next slide. So we let the elevation in boiling point be change in temperature. Okay? Then we let the mass be the Y gram, mass of the solvent be that, the relative molecular mass of the solute be M. And we see what next. How can we treat such results? When we are treating such results, we say that the X, on our next slide, X gram of the solvent dissolves in Y gram of the solute. Is it okay? We saw from the experiment that we dissolved X gram of the solute in, we dissolve the Y gram of the solute in X gram of the solvent. So in that case, X gram of the solvent dissolves. Okay? This one dissolves, the other one dissolves. Okay? So when you look from that one, we go to 100 gram of the solvent. If X dissolves Y, 1,000 grams will dissolve what? That means 1,000 will dissolve Y over X times 1,000. Then we look at the change. That the grams you get there, they are the ones which can cause a change in the boiling point. Y over X times 1,000 can cause a change in the elevation in the boiling point. Okay? Can cause a change in the boiling point. In other words, can cause an elevation in the boiling point. So what about the constant? This KB which we are talking about to be constant. Okay? The constant boiling point. Okay? Elevation. Boiling point elevation constant. KB. What is it? For it can be caused, the change can be caused by the relative molecular mass of the solute. So you look at the two. How do you move from there to the final conclusion? There. Okay? What you do, you multiply KB, you cross multiply there. KB with Y over X times 1,000. I think we should do that here. Remember, there you have that XTB caused by Y over X times 1,000. This one, the boiling point elevation is caused by that. Then we see that the boiling point elevation constant, for it, it is caused by the relative molecular mass of over solute. Okay? So what happens here, once you have those two statements, is you are going to cross multiply there. Simple. Then you get what? change in temperature times RMM of the solute, okay? So we get Y times 1000 times KB over X. So here, this one, you have change in this, you have boiling point elevation multiplying this one to get the other one. So here, what you want, if they have asked for the change in the boiling, if they have asked for boiling point elevation, this one will go the other side. Okay? So you remain with this one. If they have asked for this one will go the other side. And you remain with that. Okay? So there, the manipulation of this work depends on what you want. So let us look at example 1. This one will lead us to example 1. Example 1 on our slide 27 there. When you look at that example 1, it is saying that a solution contains 50 grams of ethane, okay, and ethane 1,2-diol, and 40 grams of water, okay. Calculate the boiling point of the solution, okay. State any assumption. They are saying calculate the boiling point of the solution. But in our expression here, we don't have boiling point anywhere. We have boiling point elevation. Okay? So we say that boiling point elevation is the difference between the boiling point of the pure solvent you subtract with the boiling point of the solution. Okay? So when you subtract the boiling point of the solution, when you subtract the boiling point of the solvent from that one of the solution, you get the boiling point elevation. Remember, the boiling point of the solution is higher than that of the solvent. So you should consider it, that this one is high. So on our next slide, we look at the summary. What you do first is you summarize whatever given. You see, you let the boiling point elevation of the solution be TB, change in TB. Okay? Then molecular mass of the diol, ethane diol. You say that is the ethane diol for chemical formula. You get 62 grams. You calculate it. This is A level. We are not going to look at it. The relative molecular mass. How to calculate the relative molecular mass is simple for all of us. Okay? Because we are measuring in what we understand most. Mass of the solute is 50 grams. Mass of water, I think, is also given. That one is supposed to be the boiling point elevation constant. So let us look at our next slide. On our next slide, before that, on that very slide, let's go back. That very slide, we see that now we start. Remember the other side we said that X grams of the solvent dissolves Y grams of the solute. So here we say what is X? The 40 grams of water dissolves the 50 grams of diol. Next we look at 1,000. Okay, on our next slide, we look at 1,000. Remember, we began with X dissolving Y. Then we looked at 1,000 dissolving Y over X times 1,000. On our next slide. So we see that 1,000 grams of water will dissolve 50 times 1,000 over 40. Then we come up with the answer 1,250 grams of diol. Then we said that, remember we said that that mass, if we can look at this one, this mass causes a boiling point elevation, this, and this one causes boiling point elevation constant. Okay, so we look at the 2. We say that 0.25, which is the constant, is caused by 62 grams, the RFM. Then the boiling point elevation will be 1,250 times that over 62. Then you get the boiling point elevation. Once you get the boiling point elevation, you look at the boiling point of water is 100. Everyone knows that one. Will not be given. If they talk about water, you know the boiling point. If they talk about a given solvent, you look at on the first page or the last page. It may be given or within the question. Okay. So the boiling point of the solution will be the elevation plus the normal temperature of the water, the boiling point of the water. The reason why it is 373 is because that we are measuring it in kelvins. So we get 100 plus 273, we get 373. So we get that answer. On our next slide, we are going to see when you use directly the formula, what do you get? You use directly the formula given. Okay? On our next slide, we use directly the formula without going through the first principles. That's what we have been looking at. Those are the first principles. But if you use a formula, this formula, look at it here on the blackboard. This formula is change the boiling point elevation times the relative molecular mass of the solute. What do you want? You want this one. So you make this one be the subject of the formula. Will equal to Kb times Y times 1000 divided by X times the RMM of the solute. So having made your summary, you can just substitute. Just substitute everything. Okay? There. You substitute and get the right answer. Let's go back to that slide. It gives us the answer. So once you substitute, you put there 1250 is the what? Is the mass of the solute. Then 62 is the relative molecular mass of the solute. X is the mass of the solvent. You put it there, you get 10.48. Then you add it to the boiling point of water and you'll be able to get the right answer. So when you go to our next slide, we see example 2. Example 2 is requiring us to calculate for the Kb for benzene and the RMM. So if you look at this one on the blackboard, what they're asking for is the Kb. So what is important is identifying that these ones are given. Roman 1, you identify that these ones are given. Okay? You identify that these ones are given. Then you remain with the Kb. Once you get Kb, you will use, remember Kb is a constant. Let us go to our next slide. Next slide is showing you that how to get Kb. Already we have discussed that one. We're not going to repeat it. Next slide. Those ones when you are getting all what is in the question. On our next slide, that one we get Kb. And Kb, you calculate it from, you can use the formula here. You get it. You just substitute what is given. You remain with only Kb, not given. Then you make Kb to be here. On the blackboard, you make this one to be the subject of the formula. That means Kb will be equal to boiling point, this one, times X times RMM of the solute divided by Y times 1000. Once you be able to make Kb be the subject of the formula, this one multiply it here, that one divide it here. As an A-level student who is doing complex mathematics, you should be able to make Kb be the subject of the formula and you substitute. On our next slide, we see that we use that KB now to get RMM. We get this one, now we substitute again. Okay? On our next slide, we are going to see the results there should be 114. Then we are seeing that there is a enable number on our next slide that we need to do, okay, as part of our assignment. That enable number was in that, it is in that paper, enable 20, 2003, paper 2. Go visit your QB and get that question. Okay, on our next slide we see the activity. That is the activity we are supposed to do. And next slide. That is the activity we are supposed to do. Please be reminded that all this work is on our website. I know time sometimes is not enough for you to copy the exercise, okay? But I have told you that you can visit, you click the next slide so that these slides be recorded in the video. Next slide. Producer. Yes, that one. That is another activity. So these activities, you are seeing that they are being recorded in our video. So you can visit our top television page and you'll be able to watch the video and do the exercise. If you cannot, visit our website www.codehighschool.ac.ug. You'll be able to access all this work. Okay? So tomorrow we are going to pick up from here. We are handling one property after the other. So immediately we come the morning, come when you have done the exercise. Do this exercise, it is for your own benefit, okay? Parents will request that you at least monitor your students, but for the A-level students, you should be self-driven, okay? You don't need to be constantly monitored. Okay, you know what you want and you know what the country needs as of now. Okay, you have been good listeners. Mine as Saul Chamanwa. Told you can visit me on the top on my Facebook page, Saul Abooki. You can contact me, the number I gave it. You can check me on Twitter. I'm all those platforms. YouTube, on my YouTube, Saul Abooki. All these videos will be there. Thank you. Let's meet tomorrow.
Television, your family network.
Bannayuganda bannange mbalamusiza nnyo, amannya gange nze Namuyimbwa Shanita abanjige mumanyi nga Bad Black. Abaana ab'obuwala naddala abali ku nsalo za Uganda n'amawanga agatwetoolodde mbasaba okwesonyiwa badreva ba trailer ne biroole mu kiseera kino nga tuli mu lutalo lw'okulwanyisa ekirwadde kya coronavirus ekitadde amawanga gonna ku bunkenke. Mbasaba obutakkiriza badreva ba trailer kubakwatako wadde okubasemberera. Mbakubiriza okugoberera ebiragiro by'abasawo n'okulungamizibwa kw'omukulembeze w'eggwanga. Singa tunaakola ekyo tujja kuwangula.